I'm masquerading as Edwin. We decided to switch up the order just to keep you all on your toes. So I'm going to continue building on what we've talked about in terms of contracts. And today I'm going to talk about gradual types and how we can, what gradual types are, what we can do with them, and how we can understand them and reason about them using some of the formal tools that we've talked about the last couple days. So to start with, what's gradual typing? Gradual typing is just combining two systems with different type systems, particular with one type system that enforces more invariance than the other one. Usually this is done with a typed language and an untyped language. So one typed system that enforces some invariance and another one that doesn't. So typed racket is the gradually typed system that I've been working on for a long time. And in that system, you write both typed components and untyped components. And that looks sort of like this. So here's the typed program that we wrote on the first day, implementing the argmax function. And just to review what's going on here, we've got a type signature right here that says exactly what this function is supposed to do, which is take a function from A to real, take a non-empty list of A, and it's going to pick an element of A that maximizes F. And this is written in a component. It's written in typed racket. So racket lets you declare what language a component is written in. That goes, as David pointed out earlier, usually on the first line right here. But we can write subcomponents, submodules, inside of our larger components, and they specify the language right here. You can see that the language, as all these arrows indicate, provides all of the basic functionality for the program. For example, the ability to define types, to require or provide identifiers, to define functions, all the basic standard library functions. So this is a typed racket component. And then over here, we have another one, another component. This module U is just written in plain racket. And it imports our argmax component. And then we can compute argmax of various things. And one important thing to note is this is not typed. There are no types in the U module. That's why I labeled it U. And it nonetheless runs just fine. So let's look at what happens with this first example. When we run it, we should successfully get 3. And there we go. There's 3. So what do we think is going to happen with this second example? Yeah.
Go ahead and say it will be a runtime error.
So it's going to be a runtime error. So that means we're not statically detecting this error. That's right. We don't have a static type system here. So there's a sort of two possibilities for what kind of runtime error we could have here. One is that if you just call argmax, then with an empty list, then we are immediately going to take the rest of that list, and that will fail if it's an empty list. So that's one possible runtime error. Yeah? Yeah, so we could get a contract violation that we've failed to live up to the specification for argmax. And in fact, that's exactly what happens. So argmax contract violation, expected a pair, and we got empty. And you can see here the contract that was violated. And this contract is what our type specification up here was turned into. So here's our function type, which is a function from A to real and a non-empty list of A to an A. And here's the contract that it got translated into. So that contract takes in a function from anything to reals, a pair of anything and a list of anything, and it returns anything at all. So far so good. Any questions about what we've seen so far? Yeah. Yeah, that's a really good point. There's a few things that we've left out of this contract that are there in that type. In what way is it weaker? Yeah? Yeah. So we talked a bunch on the first day about how parametricity tells us that this type ensures that we only return elements of the list. But this contract does not enforce that. This contract says we could return anything at all. And in fact, it says that we might call the function with anything at all, not just with elements of the list, and that the list might have anything at all in it. Any thoughts as to why we might be using this contract instead of a naturally stronger contract that seems like it fits the specification more closely?
You might want to pass it functions that naturally work on many types.
So that's definitely true. We want to have a contract that doesn't restrict us from working on any particular type. Argmax should in fact be polymorphic. It should work for any type. So we couldn't just pick a particular type and instantiate the contract there. But why not have a contract that enforces this polymorphism in some way? Do we need that? Yeah.
I don't think you can get it because you have polymorphic lists, right? So you can have a single list that has elements of a bunch of different types. So you can't, things like parametricity would be hard to establish there.
So there's definitely some trickiness with implementing parametricity. But do we need to do that? Are we losing something by not doing that? Well, let's think about this in a different way. Is there a way that we could break this contract? Who's responsible for this, the part of this contract that's this NEC that I've highlighted? Who's supposed to, so that corresponds to the A input to this function. Who's responsible for that? argmax, the argmax function. How about this? Any? Who's responsible for that? The same. These two are both the responsibility of argmax. So argmax, however, is written in our typed language. We're running our static type checker over that. So we know that argmax is only going to call our function with appropriate elements. And we know that argmax is only going to return appropriate elements because we ran our type checker. So therefore, we don't need to worry about what argmax might do. We've used the static type system to rule out those kinds of bugs. So we can have a weaker contract there. And then here we have any non-empty list. So what this just says is argmax should work for any non-empty list, and all it's going to do is call your function on it. So there's no obligations. Argmax doesn't rely on any parts of any specification on the elements of the list because argmax doesn't do anything with the list other than hand it out to the function that you passed in. So we're able to rely on the information we get from the type system to simplify this contract into the one we expected. So there we have an interesting contract that's generated from this type. So this is the second important piece of gradual typing. So we've now seen two pieces. One, we can combine typed and untyped programs in one program in a straightforward way. We don't have to write some adapter in order to use plain racket programs with typed racket programs. Yeah.
So are you saying that the contract of the type system guarantees you that the result is an element of the list?
No. So I'm saying that we know that the result is an element of the list from the types. And we also know that the result is an A from the types. So we don't need to check that at runtime. We know statically that that's going to be the case. Therefore, there's no need to check that further at runtime. The things we don't know at runtime are things like, will this function produce a real number? Will we pass in a non-empty list? So that's a case where we got this violation because we didn't pass in a non-empty list. Let's look at another error, which is this one. So here we have a function that we're providing to argmax that sometimes produces values that are not real numbers, produces false. Of course, we can't check that statically because this part of the program is not written in our typed language. But, of course, contracts, because they're enforcing this behavior and because contracts can handle higher order behavior, as we've seen, we get a contract violation. Now I'd like to point out one additional thing about this contract violation. We talked about how contracts come with blame. Contracts always identify the part of your program that violated the contract. And we see here that we blame you here. That's this component that's written in untyped racket. Now let's go back to our empty list example And let's look at who gets blamed in that case. So again, we're blaming U, which is the untyped module. And in fact, this is a general invariant. We're always going to blame the untyped part of the program. So this is, in some ways, deep theorem about this, and in some ways it's just a consistency check like type soundness. And in fact, this is really the generalization of type soundness. Type soundness for gradually typed languages means that the typed part of the program behaves consistently with its types, and that the untyped part of the program might not behave consistently with those types that you expect, in which case you'll get a dynamic error. But it's always the untyped part of the program that's responsible for the inconsistency between the behavior and the types. Yeah?
Yeah, so what happens if you pass in a non-uniform list and the function doesn't handle it?
Like that? So false was the element that maximized that. So let's think about this. I'm going to claim that this is in fact a perfectly uniform list. It just happens not to be a list of integers. There's a perfectly good type for this, and in fact, this program. This program type checks just fine. So what's going on here? What's going on here is that this is a list of a bunch of, with a type that describes all of the possible elements, but we can say that it's a union. And here's the things that we might get back. Might get false, or a string, or a number, or the list ABC. So we have typed racket supports arbitrary unions of types, and in fact, this gets back to why we didn't need, why the contract that we generated for argmax looked the way it did. Let's look at that again. So here's our contract error. And you remember we had these NECs in the contract for the list. So why don't we need to check something there? That's because the untyped part of the code could be using this at any possible type. There's nothing we can say about what that A might be instantiated at. They could pick integer or string or a union of integers and strings or functions or anything at all. There's absolutely no restrictions we are placing on what the contents of that list could be. And so we can just say list of a non-empty list of anything at all. Yeah?
What was the result of when you ran argmax?
It decided that for this rather strange implementation argmax function, that false, which was the third element, was the one that maximized the value of this function, but this function is sort of a silly index function. So if I try it again, it might produce something different. Yeah.
Why does it blame this line on the code? And it's blame false, it's
So this is where the error happens. So line 5 is where the contract is, because that's where type racket automatically generates a contract when you provide something out. So that's where the contract that fails is. So that's why it's line 5. But you'll see that it does highlight dynamically the part of the program where that happened. Yeah. So this is something from this is a error message from the more general contract system. So as we talked about last time, contracts are programs, and they could be wrong as well. So this message is to encourage you to recognize that if you get a contract error, it might not be, in fact, the program that's wrong, but the contract that's wrong. And this can happen, in fact, in typed, untyped interaction as well. If I say I expect some untyped program to have a particular type, that might be an expectation that whoever wrote that software didn't expect. We might get an error. Typed racket will blame the untyped part of the program because that's a theorem that it will always do that. But if you wrote that program, you might not expect that. So let's actually see what that looks like. So let's look at this program. This program says, we've got some code written in untyped racket. It happens to just be the add1 function. And then we have some code written in typed racket where we say, I'd like to import f, and I'd like to ascribe it the type integer to string. Now, something's going to obviously go wrong here, because this function does not produce strings. But whose fault is it, and what's gone wrong? What's gone wrong is that we specified a type that is not the behavior of this function. But it's impossible to tell from the perspective of the system what was supposed to happen here. Was this supposed to be an integer to string function that we've implemented incorrectly? Was it supposed to be a integer to integer function that we wrote down the specification for incorrectly? Or maybe something else. And therefore, we get an error message that says we're blaming the interface for f that says we specified an interface for f that didn't work with the actual behavior of f. But importantly, it's not our typed module that's to blame. And in fact, we're never going to blame the typed module. And that's the general theorem that we want to have about gradually typed systems, is that so the slogan here due to Phil Wadler is that well-typed programs don't get blamed. And in general, the only things that get blamed are untyped components that use typed components incorrectly, and interfaces for untyped components that don't line up with the actual behavior of those untyped components. Okay, any questions about what we've seen so far? Okay, so let's think about a slightly more interesting contract where we're going to write down this program. And now let's think about how we can specify the contract for this. And in fact, it's just, here's the identity function. And this should work, right? We would expect this to work. And indeed it does. Let's remember that the program which we wrote before with argmax also used a polymorphic type. But here we're doing the polymorphism on the other side. In particular, we're saying that some untyped piece of code is going to be polymorphic. And therefore, now we can't rely on the type system to ensure that really the function is going to behave according to this type. So we have to enforce that. So how might we implement this contract? First, let's see what might happen if we violate this contract. What might be a program that would, how could we change this program to violate this contract and see what happens?
Return a string from F.
Could return a string from f. Okay. F broke its own contract, blaming the interface for f. And you can see a new contract form here, which is in fact called parametric. And so we're specifying a parametric contract that's supposed to be parametric in A, and it takes an A and produces an A. But what if we did something else that wasn't parametric? What other things might we do that wouldn't be parametric with f? Yeah?
Return a 1.
Could return a 1. Indeed. So how is that possible? We had a program that returned a 1 before, and it worked just fine. Now we change the program to return a 1, and it doesn't work. Okay. So this is a puzzle. So what's something else that we could try that might illuminate this puzzle? What could we? So far, all the functions we've tried writing for f that have gone wrong have been constant functions, right? So what if we try writing a non-constant function? What might we do?
Inspect the type of x.
So this is a very interesting program, actually, and it works just fine. One thing to note here is that I believe the racket optimizer turns this into the identity function, because we know that integer question mark is a pure function, and therefore it's equivalent. This program is. We know this program is equivalent to calling integer of x and then returning x, and calling integer of x for side effect is a no-op because integer is a pure function, and therefore this gets optimized back to the identity function. But let's try. Well, what if we know it's an integer, then we return 1? And we're definitely passing in an integer, so what do people think is going to happen here? Remember, when we just returned 1, it errored. So now we're passing in 1, checking if it's an integer, and if it is, returning 1. So is this going to error? Maybe is a good answer. Answer is it doesn't. Okay. Any further programs that we might try? Any other suggestions? Yeah.
Okay, so I don't understand why it works. I would imagine, well, the X, it must be of your big union type. And the parametric contract requires the result to be of the same union type.
Oh, what big union type do you mean? I don't think there are any union types here.
You just showed me the big union type that it generates.
So that was for the list, that particular list had a union type. But everything here is, the only types here are this type and integer. There's no big unions. So we still haven't tried doing anything with x. So what happens if we, x plus 1, I like that program. Aha! Now we're getting somewhere. We get a failure, and despite the fact that it says contract violation here, you can see by the formatting of this error message that this isn't an error from the contract system. This is an internal error from plus. Plus is unhappy because we're supposed to give it a number, and we got this A4 thing. Okay, so has this given anyone an idea about what might be going on here? Yeah?
We're wrapping up x in something that says, or that limits what you can do with it.
Yeah, exactly. Turns out you can, in fact, enforce polymorphism dynamically. This is actually a result that goes back 45 years now. And to Morris 1972, for whoever's going to find that paper, posted on Slack. And the idea is, when we want to enforce polymorphism, we take the value, we put it in a box that's totally opaque, but that we can recognize when we get it back. And we hand it over. And then the only way that f can respect polymorphism is if it gives back a similar box, a box of the appropriate shape and size and color. And then we, the holders of the key to this box, unlock the box, take out the element, and now we have it back. And that, in fact, explains all of the behavior we've just seen. So first, this program, we had a box. Boxes do not support addition, so we get this error. How about the previous program? What happened here? We checked if x was an integer, but it wasn't an integer, it was one of these boxes. And so then we return x. It is indeed one of the appropriate boxes. So this function, in this case, has become the identity function because we eliminated the behavior if it was an integer. And
Flip it around. Say it's not an integer.
so this program.
Yeah.
So if it's not an integer, we're going to produce 1.
No, and then change the condition. If it's not an integer,
If it's not an integer, then produce 1, otherwise produce x.
so if it's not an integer, then we do x, otherwise 1.
So this is the same as the previous program. Not and if you can eliminate nots by swapping the branches of if. But this program also has become the identity function. We have removed the portion of its behavior that is the not the identity function, and it's become the identity function. And what about this program? This again is the identity function, and we've eliminated that. And then when we had this program, this takes in a 1, puts it in the box, then takes the box and throws it away and returns 1. But the 1 we're returning is not in the box. So our contract says, are you a box? No. Error. And that's why we get this error when we try to return 1. Because even though the thing in the box was a 1, and the thing we tried to return was a 1, they're not connected. So this function is not a polymorphic identity function. It's the constant function 1, and therefore it's violating its contract.
So with the metaphor, the boxes coming into, like if you're checking into integers, the box is coming in as something, it gets checked to see if it's an integer. Then 1 gets returned, but in that case it gets wrapped correctly.
Wait, I'm not sure I'm following your explanation. Okay. So let me try giving the explanation again. Yeah. So what happens here? What happens here is this type gets turned into a contract that does the following thing. It takes in a value, whatever value it wants, in this case 1. It puts that value in a box. Then it hands that box to F. F does some stuff, very complicated computation in order to return 1. 1 is, in particular, not the box that we just handed to F. F has, in fact, thrown away the box. So then the contract checks, F, did you give me back a box? F says, nope, I gave you back 1. And then the contract says, sorry, that's not good enough.
So I guess what I'm not understanding is why it works when you're doing the check, because it's still not returning a box, it's returning 1.
So let's think about this program. Because this program works, which is what we want. This is, in fact, the polymorphic identity function. So let's think about what happens. We create the box. We hand it to F. What does F do? F just gives it back to us, which is still a box. Then the contract says, is this a box? Yay! Good. Now I'm going to, as the contract, which has the power to do this, take the element out of the box, look, it's a 1, and give that back to whoever wanted the result of calling F. Does that help?
Can you print the box boundary?
So here we have a boxed value. So this demonstrates that we've accomplished some things that we might want from the behavior of a contract for polymorphic functions, but not everything. In particular, this isn't really this isn't totally polymorphic. We're able to print things, we're able to do various operations. It's also not totally the behavior of the original function, because we've changed some of the behavior. If you pass in, if we had a function that, if it was an integer, returned 1, otherwise returned the input, we've changed that function produces 1 if you give it 3. We've now changed it to be a function that produces 3 if you give it 3. So that's a different function. This function, without the contract, if you pass it 1, prints 1. Now it prints this weird thing with a sharp sign. So we've changed our function into something that behaves somewhat differently, which might or might not be okay depending on your feelings. But we can, in fact, formally specify what we want from gradual type systems and say that what we would like from a contract for polymorphic functions is that we get only the behavior we had before, or contract errors, which is the behavior we have in typed racket for other kinds of contracts, like contracts on lists or functions or strings. And in a little bit, I'll talk about the specifying that property as well. Okay. So any more questions about this before we switch away from demoing things and talk about meta theory? In order to do which?
I mean, that you can make a secure box that the program inspects somehow.
You need some way of performing genuine information hiding dynamically for whatever degree of genuineness you want to defend against. So if your language has reflection, then you have to decide, do you want your contract system to be a barrier that prevents reflection or not? And that's a decision that you need to make for any abstraction mechanism, including a type system. You could have a reflection mechanism that lets you inspect things without following the type discipline, or you can have a reflection system that lets you inspect things without following the module protection discipline. And those are just design choices. Similarly, if you have an FFI or an IDE or a debugger, then you have to decide if those things are going to be able to pierce the abstractions that you provide here. And for the racket reflection system is not going to be able to see inside this box, but as you can see, the printing system is able to print them, and the FFI is able to access raw memory, so you can do whatever you want. Any more questions about this stuff? Okay, so with that, I'm going to turn off the projector. Okay, so let's talk about what a formalism might look like for talking about gradual typing. And then we'll be able to talk a little bit about what our, how we might formulate some of the claims I made about the behavior of the system that we saw. So first, let's think about how we might model something that looks like typed racket. So we're going to have a grammar of programs, which is going to be a set of modules. And modules are either typed or untyped. And a program is just a sequence of modules followed by an expression. Yeah?
I'm writing a little bit bigger.
Sure. So we've got our typed and untyped modules. Is that better?
Yes.
And we, of course, have our types, which will be just the base types we had before, and function types. And we have expressions, which are either values or applications or module references. And our values are true, false, and various numbers. So I've left off type annotations on lambdas because in the simply typed lambda calculus, we don't have to have them, and it makes the syntax easier not to have two kinds of expressions. So now let's think about what our type system judgment might look like for a language in which part of the system does not have types. Left off variables. So we're going to have two judgments here, one for a program and one for a expression. So let's start with the type system judgment for a program, or an expression, sorry. So we will say that this is a totally standard type system, which just says that We look up variables in the environment. So here's our totally standard type system. I'll leave off base types for the moment, but it's important to note that I haven't given any references to untyped modules or modules at all. There's no type system for modules, and there's you're not allowed to refer to any modules. So what we're going to do is we're going to say there's in fact going to be one typed module, many untyped modules, and they can refer to the typed module, but we're not going to let them let the typed module refer to the untyped module, just because that makes our lives a little simpler. We can of course generalize this, but then we have to add something like require typed to our formalism. So now that we've got our type system for expressions, let's look at our type system for programs. And that's the judgment here. This is going to say is I'm going to say a program is OK if the program is of the following form. Program is going to be a module that's typed followed by some untyped modules followed by some expression. And this is all we need to statically check. So what things are we not checking here that we might want to check? That, for example, got checked in statically when I was working in Racket. So what are the, or a different way of putting it is, what are the possible runtime errors in this language? If we write down the operational semantics, what possible runtime errors do I have to consider that might happen inside the untyped program? Yeah, so the most interesting one is that we might have some error where we violate this type. And that's what we're going to have to do to deal with, to say something about talking about blame and whether we generate correct contracts. What other runtime errors are possible? So note that we're not checking that any of these programs are type correct. So what might go wrong with those expressions when we run them? What would go wrong to cause them to get stuck? What? So there's no type system for them. So I think they're not well typed is not really a useful thing to say about them. But like, what kinds of programs might do something bad? What's an example? Yeah, we might try to misapply a basic operation. What else? What was that?
I mean, we don't have fields, right? You couldn't try to access.
We don't have fields. This is just the simply typed lambda calculus with some base types.
You can make an application on the left-hand side that's non-lambda.
Yeah, we can. So think about this program. We have an integer, which is 7, and then our body expression is 5 applied to 2. So this is an error dynamically. And this satisfies our judgment for programs. This is just what it means to be a gradually typed system, is that we have expressions where we're not checking the types, and we have some other expressions where we are checking the types. So what else? What other possibilities might go wrong here? What other things might go wrong? Yeah? So this, we don't, this should be empty. Sorry. I'm just so used to writing gamma before my turnstiles that I do it even when it shouldn't be there.
So E can have free variables.
Yeah, so E can have free variables. It can, in fact, have two different kinds of free variables, right? It can have free module variables, and it can have free lexical variables. So we might change our judgment to rule out free variables so that we don't have to deal with free variable errors, or we might make those an explicit kind of errors in our untyped language. Note that our typed programs do not have free variable errors because we're checking the type system enforces well-scopeness, and it prevents you from writing any module variables. So, but just for simplicity, I'm going to omit the free variable checking here. We could say, but we could just say something like E closed, E closed, and then not worry so much about free variables. So there's a number of possibilities, but let's get back to the interesting one, which is we might violate the expectations of the typed module from the untyped components. So let's think about how we might enforce that dynamically. That's going to require us to do a couple things. First, it's going to require us to come up with a translation from types into runtime enforcement. And we're going to use contracts to implement that runtime enforcement. So we're going to define a translation from this language into the language that we saw before. So that's the contract PCF. And that's going to then allow us to run contract PCF and make some statements about what might happen there, and that'll tell us the things we want to know about this language. What might happen for partially typed programs. So let's define a translation from this language into contract PCF. And we're going to extend contract PCF with a slightly more general recursive binding form just to make our lives a little easier. So I'm going to write letrec for our modules. But first, let's so our translation of P I will write like this. So this is some E, but some E in CPCF, which is the language we saw yesterday. So let's think about what that translation is. So the translation of why can't I spell module? A typed module this is going to be a monitor. If we recall monitors previously, so we're going to label this monitor. The positive position is M, and I'm going to give the negative position the label U, and the contract the label M, because we wrote down the type with the program. So we can pick various things, and what we're going to want to prove is that U is always the person who gets blamed. So that's the translation and this is going to be the translation of tau, which is going to produce a contract, and the translation of E. Then the translation of an untyped module is just the translation of the expression, and the translation of a program is going to be, which this board moved as well, is going to be, I'll write letrec So what this says is the translation of a full program is we translate the typed module, we translate all the untyped modules, we translate the body, and we implement this using letrec. And letrec can be expressed in CPCF using mu, although it's rather annoying to do so. So I'm not going to write out the translation. But we've got a program that allows us to enforce this. And in particular, we've translated the typed module into a monitor where we translate the type into a contract. And let's look at what the translation of types into contracts looks like. This is, in fact, yeah?
What is B in this case?
EB is the body expression. Make that look a little more like a subscript. So translation of types into contracts is very straightforward because our types are very simple. So the translation of function types is just a function contract. And the translation of base types, maybe it'll be helpful if I write, spell them out, Booleans or numbers. So translation of Boolean is it's a flat contract that checks if something is a Boolean, and the translation of number is a flat contract that checks if something is a number. Note one thing that's important to do is to throw away the type system that we had for CPCF. Particular, when I presented CPCF, we had a type system. It's a straightforward type system. But if we're trying to embed untyped programming into CPCF, it's not going to work if we have a typed language that we're translating into. We'd have to insert lots of injections or a sum type or various other things. So instead, we're going to translate into an untyped language with monitors. And so now we have a language with contracts over effectively the untyped lambda calculus with base types. So here now we've got a contract system, and which in fact has the nice property that you can run this translation backwards, which makes some of the proofs significantly easier. So we can read off the type for the program. Now, given this translation, the translation on expressions is just the identity function. So now that we've done this, we can run the operational semantics for CPCF straightforwardly. And of course, CPCF includes contract errors. So what can we say about the contract errors? In particular, what we can say is that we have this distinguished typed module, and its label is M. And we can say that if we have a well-typed program, so I'll write down the theorem. If we have P and it's OK, and we run P to some contract error, then L is not M, where M is the label of the typed module. So we can extract that label in various ways. But so this is what is known as the Blame Theorem, that if we have a appropriately typed, gradually typed program, then running it does not blame the typed part of the program. It might blame other parts of the program, and it might diverge, might error in some untyped part of the program, but we're never going to violate this contract that we've generated from the type system. There's actually something else we might want to say, which is that the regular type errors that we get don't happen in the typed module either. We don't have a situation where we apply 5 to 2 in the typed module. That's something that's also ruled out by the type system. So how can we prove that? The way to do that is when we go from a typed version of CPCF to an untyped version, we need to say something about what happens when we have an error like this. And the way we do that is we're going to label all of the expressions in our program with what module they originated in. And so we're going to say every expression comes with a label. So we'll label our and then we're going to have reduction rules that will look like this. If we've got we add reduction rules like this for each possible runtime error, which is in fact, this is the only runtime error that's really important here is because we don't have any operations on our base values. But we say the label here comes from the label on the application, so we know which module was it that applied the wrong value. And once we have that, then this theorem, the Blame Theorem, tells us, in fact, that our type system did the right thing, and that our program successfully enforced the boundary between typed and untyped programs. So we don't get any runtime type errors from the type module, but of course we might get them from any of the other parts of the program, and we don't get any type errors from the interaction between typed and untyped programs. So this is the blame theorem. Just to say a brief thing about how you might go about proving this, there's been a number of different proof techniques for this theorem. Turns out the meta theory and techniques that we talked about yesterday involving complete monitoring and blame correctness are really useful for doing this. That the fundamental property that you want is that all the interactions between the typed part of the program and the untyped part of the program are monitored by the contract, that the typed module is only responsible for being blamed if values it produces violate the contract. That's blame completeness and blame correctness. And then you just have to prove that it only produces values that satisfy those contracts, those flat contracts. But that's a straightforward consequence of the type system, because we've already checked that. And we can look at the contract, see that, read off the type, and check that our program actually matches that type, which it does, given the translation that we defined for types to contracts. OK. So one final thing that I want to mention is I said that the translation of polymorphic types to contracts is not 100% satisfying. And that's because it changes the behavior of programs in some ways. So how can we characterize that in this framework? Well, what you might want to say is, what if we had an entirely untyped program? We didn't have the typed module. And we ran that program, and it gave us an answer. Then we add types to one of the modules, and we run the program again. What answer do we get? Now, of course, we might get an error. Because if our program was passing a string through a function, and we say that function only accepts integers, then if our function was the identity function to start with, then we'll now get a dynamic contract error, even though the program would have worked before. Or we might get the same answer if our contracts just allow the behavior we have. Or if we've done something wrong, we might get a different answer. And you would sort of not like to get a different answer. But that's exactly what happens with the polymorphic contracts. Some programs turn out to produce a different answer. They still satisfy this blame theorem, but they might produce a different well-typed answer at the end. Or they can't possibly violate the contract, can't possibly blame the typed part of the program, but they might give us a different answer. And so that's a criteria we might want for programs, but it's a criteria that this implementation of polymorphic contracts does not satisfy. And that criteria is called the gradual guarantee, or it's actually half of the gradual guarantee. So that's another criteria that we might want, that this language that I've just presented satisfies, but that as you add more complex features to your type system, and then similarly you add those features to the contract enforcement mechanism, it can be harder to satisfy. So these are two different criteria that you want your system to satisfy when you're interacting typed and untyped parts of your program. And fortunately, Ron is going to talk lots more about all of these topics in the next few days. But that's it for me. Thank you very much.